A Sherman tank came to a halt in the desert, its track sinking slightly into the sand. Beneath the hastily painted German cross, the American star still showed through in places. Officers from Battalion 501's heavy companies gathered around this remarkable prize, already holding notebooks, preparing to document what they'd found. This single intact and operational American tank, captured during the Battle of Kasserine Pass, would spark something far more significant than a tactical victory. It would trigger a crisis of confidence that rippled through German engineering departments and tank development programs for years to come. The mathematics of armored warfare were about to shift, not because of superior firepower or thicker armor, but through something the Germans had fundamentally underestimated: automotive excellence that simply refused to fail. The tank bore the name War Daddy II painted across its hull, serial number USA 3067641, built by Lima Locomotive Works. It belonged to Company G of the 1st Armored Regiment, 1st Armored Division. German personnel from a reconnaissance unit drove this Sherman across 350 kilometers of North African terrain to reach the port of Sfax. 4.5 days of travel lay ahead, and every single kilometer would challenge German assumptions about American industrial capability. The engine never overheated, the transmission never failed. The final drives maintained consistent performance throughout. German tank crews, accustomed to frequent mechanical stops, even on short movements, watched with growing unease as this enemy vehicle simply worked. It moved without complaint through terrain and conditions that would have crippled their own equipment. At Sfax, War Daddy II was loaded onto a cargo ship bound for Germany. The Army Weapons Office had issued explicit orders. This tank had to reach the testing facility at Kummersdorf intact and operational. German intelligence had received fragmentary reports about American tank production, but seeing the physical vehicle made those statistics real in ways that numbers on paper never could. The Sherman represented mass production at a scale Germany couldn't match, built with automotive engineering principles Germany hadn't mastered. As the ship steamed northward across the Mediterranean, German engineers prepared testing protocols that would reveal truths they'd been reluctant to face about their own limitations and American capabilities. By spring 1943, the tank had arrived at Kummersdorf, the proving ground located 25 kilometers south of Berlin. It rolled off the transport rail car bearing the designation Versuchskfz 259 and German license plate WH05941. Test engineers had already stenciled armor thickness measurements and angles across every surface, marking it with precise notations for their comprehensive evaluation program. This facility served as the primary testing ground for both German and captured Allied equipment. Here, meticulous engineers measured, tested, and analyzed everything from track tension to transmission efficiency, documenting findings in exhaustive technical reports. German test engineers conducted the initial inspection with specialists from multiple technical branches. They photographed every component from dozens of angles, measured every clearance with precision instruments, undocumented construction techniques that seemed impossibly straightforward compared to German methods. The transmission caught immediate attention from powertrain specialists. German tanks employed straight-cut gears requiring precise tolerances and frequent maintenance. The Sherman used herringbone-cut gears that distributed stress across multiple teeth simultaneously. This design, standard in American automotive manufacturing since the 1930s, provided exceptional durability with minimal precision requirements. German engineers had considered herringbone gears too difficult to mass-produce given their industrial capabilities and workforce training. The Americans had been manufacturing them by the thousands. Testing began with basic automotive trials designed to stress every mechanical system under controlled conditions. Engineers drove War Daddy II through obstacle courses designed to replicate battlefield conditions, recording fuel consumption, monitoring engine temperatures, and documenting transmission behavior under varying loads and terrain. After each trial, they disassembled components to examine wear patterns, looking for signs of stress, inadequate lubrication, or design weaknesses. The results contradicted everything German tank doctrine had accepted about necessary trade-offs between performance and reliability. The Sherman performed adequately in every category and excelled in the one metric: German tanks consistently failed. Operational endurance without maintenance intervention. The powertrain examination revealed design philosophy differences that explained much about American versus German approaches. The Sherman transmission featured 5 forward speeds plus reverse, with synchronization in gears 2 through 5 that eliminated the need for double clutching during normal operations. This made the tank nearly as easy to drive as civilian automobiles, requiring minimal specialized training for drivers. German tankers, by contrast, spent considerable time learning complex double-clutching techniques and careful throttle management to avoid damaging their transmissions. The Sherman's design accepted that ordinary soldiers with basic automotive knowledge would operate these machines. German designs assumed highly trained specialists would be available. The Continental R975 radial engine in this particular Sherman demonstrated remarkable tolerance for varied operating conditions. Engineers noted that the engine maintained consistent performance across temperature ranges that would have caused German engines to overheat or lose power. The cooling system, though simple in design, proved highly effective. The air filtration system handled desert sand without the frequent clogging that plagued German tanks in North Africa. Every system reflected a design philosophy that prioritized practical functionality over theoretical optimization. By June 1943, Reichsminister Albert Speer arrived to preside over a major armaments conference, attended by leaders from industry and senior Wehrmacht officers. The demonstration program included hill-climbing trials comparing German and captured Allied tanks. War Daddy II sat alongside the latest German designs, including a Panther D medium tank fresh from production and a Ferdinand tank destroyer representing Germany's most advanced armored fighting vehicle technology. Speer, responsible for German armaments production and personally accountable to Hitler for results, needed to understand what American industry could produce and how German designs measured against enemy equipment. The demonstration would provide answers neither Speer nor German tank designers wanted to acknowledge. The Sherman climbed the test slope smoothly. Its manual transmission with 5 forward gears, synchronized from 2nd through 5th, shifting without hesitation. Its engine maintained consistent power delivery throughout the ascent. The driver handled the vehicle with confidence, demonstrating the ease of operation that would become a Sherman hallmark. The Panther followed, its more powerful 700-horsepower Maybach HL230 engine, allowing it to match the Sherman's performance, but only barely and with considerably more difficulty. The Ferdinand, massively heavy at 65 tons and technically sophisticated with its electric transmission system, stalled partway up the incline. Speer watched as recovery crews struggled to restart the vehicle. The embarrassing failure occurred before dozens of senior officers and industrial leaders. Years later in his memoirs, Speer would write about Sherman capabilities he observed during his inspection tour of Italy in October 1944. He noted that reports on the cross-country mobility of the Sherman had been very favorable, with the tank climbing mountains German tank experts considered inaccessible to tanks. He attributed this to the Sherman having a very powerful motor in proportion to its weight, giving it cross-country mobility on level ground that was definitely superior to German tanks. The 26th Panzer Division had specifically reported this advantage. These observations from Germany's armaments minister carried significant weight within Wehrmacht circles. The written public assessment appeared in Das Reich newspaper on June 27, 1943. The article described the Sherman as one of the special accomplishments of North American laboratories and called it a praiseworthy product of the North American steel industry. The article noted that the first things to attract attention were serial construction and fulfillment of the almost arrogant requirements of the North American automobile industry. The piece mentioned the gyro-stabilized gun as the first attempt of its kind ever to be made anywhere, acknowledging American innovation in this area. These public statements, carefully worded for propaganda purposes to avoid appearing defeatist, nevertheless concealed the private alarms spreading through German engineering departments. American tanks weren't just adequate, they were fundamentally better engineered for sustained field operations. Back at Kummersdorf, systematic testing continued through summer and into autumn of 1943. Engineers measured the Sherman's operational range, conducting extended trials that pushed the vehicle to its limits. They documented operational ranges exceeding 2,000 kilometers before requiring major maintenance, roughly 4 times what early model Panthers could achieve in field conditions. They measured transmission efficiency that exceeded any German tank, with power losses through the drivetrain significantly lower than comparable German systems. They examined the synchronized manual transmission that made gear changing smooth and simple, requiring neither the double clutching nor the careful rave matching that German transmissions demanded. The final drives presented another revelation that challenged German engineering assumptions. German Panther tanks employed final drive systems inherited from the Tiger design, a configuration prone to failure under stress. The design used straight-cut gears in housings that proved inadequate for the loads imposed by the 45-ton vehicle. German mechanics in North Africa and on the Eastern Front had reported final drive breakdowns, forcing Panthers to be abandoned after relatively short movements, sometimes less than 100 kilometers. The Sherman's final drives, built using the same herringbone gear principles as the transmission, rarely failed even under sustained combat conditions that would destroy German components. Restoration projects decades later would find Sherman final drives that needed no mechanical restoration after years of storage, testament to design margins that exceeded immediate requirements by substantial factors. By late 1943, Kummersdorf had accumulated enough data to produce comprehensive internal reports that circulated through Wehrmacht technical branches. These documents, intended for senior Wehrmacht officers and armaments ministry officials, painted a sobering picture of comparative capabilities. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked despite its theoretical knowledge and scientific expertise. Mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing, yet resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training, while German vehicles required factory-level precision and specialized equipment for many repairs. The entire design philosophy prioritized keeping vehicles operational rather than achieving theoretical performance maximums that looked impressive in specifications but couldn't be maintained in combat. Internal German engineering assessments documented observations about American industrial advantages that went beyond simple production numbers. American automotive engineering reflected decades of civilian industry experience that Germany had never developed at comparable scale. Before the war, the United States had widespread automobile ownership, with vehicles commonplace among ordinary citizens across all economic classes. Germany had far more limited civilian automotive experience, with cars remaining luxury items for the wealthy and party elite. The Volkswagen program promised to German workers since 1934 had delivered fewer than 1,000 civilian vehicles by 1939. This vast difference in automotive industry maturity translated directly into tank design philosophy. Americans built tanks that mechanics with civilian automotive training could maintain using skills they already possessed. Germans built tanks that required specialist training and constant expert attention from personnel with years of specific military technical education. The stark contrast between German and American tank engineering became impossible to overlook as 1943 turned into 1944 and the reports kept flowing in from the field. Panthers demanded careful handling to prevent their mechanical systems from failing catastrophically. The men driving them received strict orders, telling them not to shift gears constantly because doing so would tear up the transmission beyond repair. Third gear presented a particular nightmare. It would snap off so frequently that the manuals actually warned crews to avoid using it whenever they possibly could. The tanks faced another severe limitation. They simply couldn't turn while reversing without destroying the transmission entirely. Only when both tracks encountered equal resistance on the ground could they perform pivot turns, which meant their tactical mobility was severely compromised in real combat situations. When dirt or debris got sucked into the running gear, it could jam the drive sprocket and force mechanics to spend hours taking things apart to clear the damage. These failures kept happening even though Panthers rolled off assembly lines in proper factories built just for tanks, made by experienced workers using the finest materials Germany could acquire. Meanwhile, the Sherman came from a completely different background. General Motors, Ford, and Chrysler's automotive engineers had designed it, drawing on the mass production techniques they'd perfected over decades making civilian cars and trucks. These American companies built the Sherman with commercial vehicle parts wherever they could. They pulled from existing supply chains and leaned on manufacturing knowledge they'd built up over years. The transmission itself came from different manufacturers, including Caterpillar Tractor, Buick, and Ford Motor Company, all building to the exact same specifications, so parts could swap between them without any adjustments needed. This kind of standardization was normal in American auto manufacturing, but remained mostly just an idea in German tank factories. When different German companies made components, they'd introduce little variations that meant parts wouldn't actually fit together properly. Through 1943 and 1944, more captured Shermans reached the testing grounds at Kummersdorf. Some came from British forces in Italy, others from Soviet units retreating on the Eastern Front. Every single captured tank went through the same careful examination process, building up a detailed picture of American tank design across different models and production runs. The British had taken some Shermans and fitted them with their powerful 17-pounder gun, creating what they called the Firefly variant and solving the Sherman's biggest problem, its relatively weak main armament. German engineers studied these modified tanks with real interest. They noticed how the Sherman's turret could actually fit a much bigger gun without needing major changes to the hull. This suggested growth potential that the original designers had built in, something the German engineers hadn't really thought about when designing their own vehicles. The Panther, rushed into production to fight Soviet T-34s, had no room for upgrading its gun at all. Any serious armament improvement would mean redesigning the entire turret and possibly the whole tank. The testing program grew to include special reliability trials meant to copy what happened in actual combat. Engineers drove Shermans for hundreds of kilometers across rough terrain, writing down every mechanical problem that happened, every repair needed, every part that failed. They then compared these findings with real reports coming back from Panther and Tiger units actually fighting in Italy and on the Eastern Front. The data painted an unmistakable picture about which tanks actually worked. Panthers had an operational readiness rate that stayed below 40% through most of 1943, with some units hitting truly awful numbers like 20 or 25%. Some Panther battalions actually documented periods when fewer than one tank in 5 could even participate in combat. Shermans, by comparison, stayed available at much higher rates no matter where they were fighting. German field reports themselves documented just how bad the Panthers' problems were. During Operation Citadel at Kursk in July 1943, Panthers managed only 16% operational readiness, with mechanical breakdowns destroying more tanks than anything the enemy did. By December that year, the figure crept up to just 37%. The February 1944 reports showed 37% again. April 1944 reached 50%. Then May 1944 finally hit 78%. These numbers represented actual tanks that could fight on any given day, with all the rest either broken down, waiting for parts, or stuck in repair shops. The improvement over time showed they were fixing problems, but even at their best, Panthers never reached the reliability levels Shermans achieved right from the start in 1942. By late 1943, anybody looking honestly at the numbers could see what was happening. The diesel version of the Sherman could run for over 3,000 kilometers before needing an engine overhaul if properly maintained. Panther engines barely managed 1,000 kilometers, and that was even after they fixed the worst early problems. German reports from March 1944 claimed that their improved Panther engines now achieved 700 to 1,000 kilometers of service life, and they presented this as a major success. Yet this improvement only brought Panther engines up to about one-third of what the diesel Sherman could do. Sherman transmissions needed basic maintenance between overhauls, but had synchronized gears that kept driver mistakes from doing as much damage. Panthers needed constant watching and frequent repairs. The third gear failure problem became so common that drivers simply learned to jump from second gear straight to fourth, skipping the broken ratio entirely. Sherman final drives worked reliably, even under conditions that would destroy Panther final drives after just 100 to 200 kilometers of operation. German units using captured Shermans reported the same results that the Kummersdorf testing had shown, and those field reports came from actual combat experience. German mechanized units, desperate for vehicles that wouldn't break down as their own inventory deteriorated, snatched up any intact Shermans they captured. Unlike Soviet T-34s, which Germans substantially modified before using them, Shermans simply went into service as is without changes. They didn't need modification because the design was fundamentally sound, with no major flaws requiring fixing. Tank crews who'd suffered through multiple breakdowns in their own vehicles found Sherman reliability genuinely impressive. Letters and reports from these men frequently remarked on how well the American tanks worked. Panzer Regiment reports noted that Sherman operators could concentrate on tactical decisions and actual combat. Panthers and Tigers, meanwhile, kept their crews in constant anxiety about whether they'd reach the battlefield without breaking down or could finish their mission before mechanical failure left them stranded. In January 1945, during Operation Nordwind, the 10th SS Panzer Division captured 12 M4A3 Shermans near Herlisheim. These vehicles had belonged to the American 43rd Tank Battalion before their crews abandoned them during the German offensive. The division organized these 12 tanks into the 13th Company of the 10th SS Panzer Regiment and put them into combat for the rest of the war. They served as scouts and mobile reserves, work that required continuous movement without stopping for repairs and meant relying on mechanical dependability. German commanders understood what years of Kummersdorf testing had already proven. American tanks simply worked when you needed them to work. This reliability, more than superior guns or thick armor, became the crucial factor in those final months of fighting. A Sherman that arrived at the battle line with a functioning gun proved infinitely more useful than a Panther with a better gun that sat 20 kilometers behind the lines waiting for repairs. As 1944 advanced and German forces retreated across multiple fronts, Kummersdorf received more captured equipment and expanded their testing programs further. Engineers examined the M4A1 with its Continental R975 radial engine and recorded its performance compared to other models. They tested the M4A2 with its twin General Motors diesel engines, noting the superior fuel efficiency and different operation characteristics. They assessed the M4A3 with the Ford GAV8 gasoline engine, which American crews regarded as the finest Sherman power plant option. Every single variant showed the same core trait: excellent mechanical reliability built on sound engineering and quality manufacturing. The consistency impressed German engineers, who were used to seeing major quality differences between different manufacturers supposedly building identical parts. The diesel-powered M4A2 particularly caught their attention. Soviet forces had received 4,102 of these through Lend-Lease, and significant quantities fell into German hands during Eastern Front retreats. The twin GM diesel engines matched any Sherman variant's performance while burning substantially less fuel than gasoline engines, critical when fuel became scarce. German designers had tried diesel engines in tanks but given up because of manufacturing complications and how complex fuel injection systems were. American factories produced diesel Shermans alongside gasoline versions without disrupting their production schedules, showing manufacturing flexibility and technical knowledge that German industry simply never managed during wartime. In March 1944, General Heinz Guderian, the Inspector General of Panzer Troops, issued official communications celebrating that Panther reliability improvements had finally reached what he called acceptable standards by early 1944. Engine life had reached 700 to 1,000 kilometers, and final drive problems had been mostly solved through design changes and better manufacturing. This achievement got presented as a major German military success, yet it merely brought Panthers up to where Shermans had been since initial production in 1942. The German army was essentially celebrating reaching standards that American tanks had surpassed years earlier, showing just how far German armor development had fallen behind. The comparison grew increasingly bitter as German tank production faltered under mounting shortages and Allied bombing campaigns intensified. The bombing campaigns methodically destroyed key parts of the German tank production system, with growing effectiveness. The Maybach engine factory in Friedrichshafen took severe damage when Royal Air Force Bomber Command struck it on the night of April 27 and 28. Over 300 aircraft participated in the raid, and Imperial War Museum records describe it as the most destructive attack on German tank production throughout the entire conflict. The same attack also hit the adjacent ZF transmission factory. Both engine and transmission manufacturing simply stopped for half a year. When production restarted in November 1944, quality had dropped noticeably. Slave laborers, increasingly used as German workers, got conscripted for the military, deliberately sabotaged components. They stuffed cigarette filters into oil passages, installed fuel components incorrectly, assembled parts without proper spacing. These deliberate failures never touched German production back in America. Located far from any bombs and staffed by workers earning good wages and working under decent conditions, genuinely motivated to do quality work. The real difference between American and German tank manufacturing wasn't about engineering knowledge. German engineers understood automotive principles just as well as Americans, and they possessed extensive theoretical knowledge and scientific training. They simply never consistently applied those principles to tank design. German tanks emphasized specifications that looked impressive but performed poorly in actual field conditions. The Panther's powerful 75mm gun and thick front armor came at the price of a power plant that couldn't reliably handle the vehicle's 45-ton weight. The Tiger's impressive capabilities required intricate maintenance and frequent repairs by specially trained technicians. These trade-offs might have worked if Germany could manufacture enough tanks and produce enough spare parts to maintain them. That simply wasn't possible, especially as bombing increased and raw material supplies tightened. American engineers trained in automotive mass production through decades of civilian manufacturing experience designed tanks that could be produced in enormous quantities and maintained by mechanics with basic training using skills from civilian work. The Sherman power plant used components already proven in commercial vehicles, with design principles taken straight from car and truck manufacturing. The electrical system included a backup generator that could power the turret traverse even when the main engine died. A feature German designers thought was unnecessary luxury, but which proved extremely valuable in combat. German tankers desperately wished for such conveniences, particularly those who'd watched their turret traverse stop functioning when engines stalled going uphill. These conveniences never appeared in German specifications because German designers never prioritized them against armor thickness and gun power. By spring 1944, German units on all fronts faced increasing mechanical problems as manufacturing quality slipped and spare parts grew harder to find. Panthers couldn't move more than 100 kilometers under their own power without their final drives failing, so they had to ride on rail transport for longer distances. Field commanders issued strict orders limiting Panther movement to conserve vehicles for actual fighting instead of watching them break down during approach marches. The Berger Panther recovery vehicle, built on a Panther chassis to rescue disabled Panthers, suffered from the same reliability problems as the tank it was designed to save. German commanders confronted the harsh reality that mechanical failures eliminated more tanks than enemy action. Some units reported that 70% of tank losses happened from breakdowns rather than combat damage. Meanwhile, across the Atlantic, German production capacity faced an impossible challenge. American factories manufactured 49,324 Sherman tanks during those war years, a staggering output that exceeded the entire German tank production of every single type put together. The British Commonwealth nations received thousands more through Lend-Lease arrangements, stretching American generosity across the globe. Over in the Soviet Union, they took delivery of more than 4,000 diesel variants. Down in Burma, Chinese forces operating Sherman tanks demonstrated the vehicle's devastating capability against Japanese armor that lagged far behind both American and German designs technologically. Wherever the Sherman appeared, from North Africa to Europe to the Pacific, it vindicated what the engineers at Kummersdorf had discovered through their meticulous testing. When maintenance crews kept these Shermans running properly, they operated reliably under circumstances that would have crippled or destroyed their German counterparts. German tank crews who managed to capture and use Shermans were almost universal in their praise. Letters, official reports, and interviews conducted after the war all sang the same tune. These American machines possessed automotive excellence that German designers had overlooked. Mechanics working on the Eastern Front reported something remarkable. They found even the complicated Chrysler 57 multibank engine, with its 5 separate engine blocks, simpler to diagnose and repair compared to the finicky German tank engines that demanded specialized expertise and equipment most field units simply didn't have. The Ford GAA F8 engine earned respect from Allied crews for its outstanding dependability and power delivery. German mechanics, accustomed to struggling with Maybach engines that needed constant tweaking of valve clearances, ignition timing, and carburetor settings, found the Ford engine refreshingly straightforward. Then there was the General Motors twin diesel, the very engine the US Army had initially rejected as unreliable and relegated to Lend-Lease vehicles destined for Allies. This diesel proved significantly more capable and durable than anything German factories had managed to produce for tank applications. The Sherman's generous engineering margins provided yet another advantage that German technical minds gradually came to appreciate. The transmission and final drive components, originally engineered for the 30-ton M4, carrying 400 horsepower, needed virtually no changes when fitted into the heavier 42-ton M4A3E2 jumbo assault variant, with its dramatically increased armor plating. These same components successfully transmitted 650 horsepower from experimental engines without breaking or requiring reinforcement. German engineers typically viewed this kind of overbuilding as wasteful, excess capacity that drove up production expenses and consumed materials in short supply without providing immediate tactical benefit. American engineers saw things differently. They recognized that design margins created room for future improvements and guaranteed field reliability that justified the additional investment throughout a tank's entire operational life. By summer 1944, German tank commanders preparing to face the Allied invasion across Normandy fully grasped their technical predicament extended far deeper than individual tank capabilities. American artillery dominance, devastating air support, and logistical might simply overwhelmed German forces, regardless of what specifications their tanks carried or how skillfully commanders deployed them. Yet the Sherman's dependability permitted American armored formations to sustain operations continuously, something German panzer divisions couldn't replicate. American tank battalions could strike, maintain combat momentum, pursue retreating enemies, and prepare immediately for the next operation with minimal maintenance downtime. German panzer divisions had to carefully preserve their limited combat-ready vehicles, knowing every movement consumed irreplaceable component life and pushed mechanical failure inevitably closer. This availability gap determined everything: which side could maintain aggressive pressure and which had to carefully ration its combat strength. When German forces captured Sherman tanks, they gained final confirmation of American manufacturing superiority. The 150th Panzer Brigade, specially organized for infiltration missions during the Battle of the Bulge in December 1944, actively sought captured American vehicles to help disguise their intentions and movements. German planners specifically wanted Shermans because of their well-earned reliability reputation. Yet the brigade obtained merely 2 Shermans, and only one actually functioned well enough for operations. That one serviceable Sherman never participated in combat anyway. Massive traffic congestion prevented the infiltration operation from ever accomplishing its objectives. For operations demanding vehicles that functioned flawlessly while operating far behind enemy lines without any nearby support, only American equipment offered genuine prospects of success. German tanks, even at peak operational condition, couldn't guarantee the sustained performance such missions demanded. January 23, 1945, marked the moment German leadership finally admitted publicly what engineers had privately known. A Panzer Commission meeting produced a report exposing catastrophic transmission failures affecting every German tank model. The numbers told a grim story. Heading into the 1945 Eastern Offensive, the Germans counted 500 defective transmissions in Panzer IV tanks, 370 in Panthers, and approximately 100 in Tigers. The Hetzer tank destroyer, built on the Czech 38-ton chassis, had suffered roughly 200 transmission failures as well. General Wolfgang Tomale, serving as General Lieutenant and Chief of Staff under Guderian, articulated the combat consequences in language stripped of all ambiguity. Under these circumstances, orderly tank deployment became essentially impossible. Soldiers stopped trusting their vehicles. In numerous instances, they simply walked away from perfectly intact tanks purely because of transmission problems, terrified they'd become immobilized and captured. German tanks, manufactured specifically to intimidate through impressive specifications, failed at the most basic requirement armored vehicles must meet: mechanical reliability sufficient to reach combat and accomplish missions. Kummersdorf's testing facility faced evacuation in early 1945 as Soviet forces surged relentlessly westward toward Berlin. Engineers worked frantically packing test data and shipping documentation to Western locations, desperately attempting to preserve technical knowledge for later examination. At least 2 captured Shermans, along with other vehicles, got pressed into emergency combat service, with units trying frantically to slow the Soviet advance toward Berlin. These machines fought alongside German designs through the final agonizing battles. The Shermans continued operating until enemy fire destroyed them or fuel supplies dried up. Panthers and Tigers, the few surviving examples still operational, broke down from mechanical failures at frequencies that horrified even crews long accustomed to unreliability. War Daddy II and the numerous other Shermans examined at Kummersdorf embodied one of World War II's starkest industrial contrasts. German engineers, functioning within an industrial system, prioritizing theoretical perfection over practical application, engineered tanks that looked outstanding on paper, yet failed during sustained field operations. American engineers, drawing from generations of automotive manufacturing experience applied to military requirements, created tanks lacking theoretical sophistication in numerous areas, yet functioning dependably under conditions that defeated German equipment. In armored warfare, as in military operations generally, the weapon functioning when required surpasses the theoretically superior weapon that cannot reach the battlefield or accomplish its mission. Post-war analysis by American and British intelligence confirmed precisely what Kummersdorf testing had demonstrated. Detailed examinations of destroyed German tanks revealed mechanical breakdowns as common as combat damage in explaining tank losses. Fractured transmission housings, transmissions frozen from inadequate lubrication, engines burned from overheating and oil starvation. German obsession with individual tank superiority and impressive statistics blinded them to reliability and maintainability's critical importance. They manufactured tanks that ordinary conscript mechanics couldn't maintain without extensive specialist training, powered by engines requiring constant skilled technician attention, sustained by logistics systems that collapsed under the accumulated burden of supplying countless different components to scattered units. Kummersdorf's testing lessons directly shaped German tank design philosophy in post-war West Germany's Bundeswehr. When the Federal Republic initiated Leopard 1 main battle tank development during the 1950s, designers deliberately prioritized reliability and maintainability over raw performance. They examined American automotive engineering principles and deliberately incorporated them into military vehicle design. The resulting Leopard 1 embraced many philosophies underlying Sherman's success: sturdy powertrain with substantial design margins, simple maintenance needing minimal specialist tools, standardized parts enabling swift field repairs, future upgrade potential without requiring complete redesign. The Leopard 1 emerged as one of Cold War history's most successful tank designs, eventually serving numerous militaries and staying in production for decades. The captured Shermans at Kummersdorf, including War Daddy II, bearing its distinctive marking still visible on the hull, signified far more than enemy equipment subjected to technical analysis. They demonstrated tangibly that industrial maturity and sound engineering, rooted in practical experience, outweighed theoretical technical innovation, pursued without regard for manufacturing reality. German designers pursued advanced specifications, believing superior technology could overcome material shortages and numerical disadvantage. They miscalculated fundamentally. American designers produced reliable vehicles because they recognized through hard experience that logistics, maintenance capability, and sustained operational availability determined modern mechanized warfare's outcome. They proved correct, and their philosophy proved decisive. The reliability disparity between Sherman and German tanks influenced more than tactical armored engagements. It fundamentally reshaped understanding regarding military industrial capacity and its decisive significance in modern conflict. Germany opened World War II possessing technical advantages across many weapons systems, commanding scientific knowledge and engineering capabilities exceeding most adversaries. However, Germany lacked the industrial depth and manufacturing sophistication, maintaining those advantages through sustained mass production simultaneously, while fighting across multiple theaters. America entered possessing weapons less technically sophisticated across numerous respects, yet possessed industrial capacity, manufacturing them in overwhelming abundance, while continuously enhancing quality, reliability, and performance, drawing from combat experience feedback. This industrial philosophy, perfectly demonstrated through Sherman design and manufacturing, proved substantially more effective than German technical sophistication applied to restricted production scales. America produced almost as many Shermans as Germany produced tanks of all categories combined, while simultaneously producing vast quantities of every other weapon, supplying allies through Lend-Lease, and maintaining living standards superior to every other combatant nation. This economic performance, unachievable for Germany even before bombing campaigns intensified, resolved the war's result as decisively as any battlefield engagement. The mathematics proved straightforward and brutally evident. A Sherman carrying a 75mm gun that reliably reached battle and fought effectively outweighed infinitely a Panther with superior armament that broke down before engaging or demanded 3 maintenance days for every operational day. A tank battalion with 80% vehicles operational could execute missions a battalion with 40% simply couldn't contemplate. Reliability transcended convenience or secondary consideration. It constituted operational effectiveness's foundation, determining whether armored formations could execute assigned missions. German tanks consistently disappointed this fundamental requirement throughout the war. American tanks consistently satisfied it. Kummersdorf's testing had proven this conclusively by mid-1943, even while German commanders deployed Panthers and Tigers, appearing fearsome and carrying impressive statistics, yet unreliable when needed most critically. The Sherman didn't triumph through superior firepower or armor specifications. It triumphed through industrial superiority manifested as mechanical dependability, consistent operational status, and maintenance simplicity. Kummersdorf engineers understood this by mid-1943 from comprehensive testing. They prepared detailed documentation recording discoveries. They verified the evidence repeatedly through scientific methodology. They reached accurate conclusions regarding American advantages. Yet comprehending difficulties and resolving them represent fundamentally different undertakings. German industry lacked capacity retooling production according to reliability principles, while simultaneously losing a multi-front war against resource-superior opponents. American industry had embedded reliability throughout civilian automotive sectors across generations of commercial competition, simply extending those established principles to military production with remarkable effectiveness. War Daddy the said, that single Sherman captured in Tunisia, tested exhaustively at Kummersdorf across months, conveyed the complete narrative through mechanical dependability and consistent function. Each kilometer accomplished without failure demonstrated German tank design, pursuing fundamentally misguided paths by emphasizing specifications over dependability. Each test validating American automotive excellence confirmed industrial maturity and practical manufacturing experience outweighed theoretical performance calculations. Each Sherman-to-German tank reliability comparison proved Americans had solved issues German engineers hadn't recognized requiring solutions. The tank itself remained unremarkable in many respects, merely one among 49,000 manufactured. Yet symbolically it represented devastation to German morale, irrefutable evidence Germany had already forfeited the industrial competition even as fighting persisted. demonstrating American productive might transcended German technical sophistication or tactical expertise.